This is the PowerPoint about minerals. Make sure you have your notes, something to write with, and then remember as you go through the PowerPoint to make a question so that you've got it to bring back to the class to write up on the board so we can talk about it. What is a mineral? A mineral must be all of the following. 4 different things. Naturally occurring, so it's got to be made in nature. Inorganic solid, meaning it's not made of anything that was ever living, and obviously it's a solid, not a liquid, not a gas. It has a definite structure and a definite composition. Composition means what it's made of. Who studies minerals? A mineralogist studies minerals and their properties. It's actually a profession, so you could be a mineralogist. What is a crystal? A crystal is a solid in which the atoms are arranged in repeating patterns. So a lot of the times you're going to have these crystalline patterns. Like if you look on the far right side of your set of notes, we've got pictures of all of the different types of crystal and shapes that the minerals can come in. And then here's that picture again, the crystal structure. Here are the 6 crystal systems that all minerals belong to. They can either be cubic, like halite or sylvite. Halite you'll actually see when we do the mineral lab in class. Hexagonal, like a hexagon. An emerald or graphite. You'll see graphite in the lab. I'm not going to give you any emeralds. Tetragonal. Tetra means 4, so it's like 4-sided. Wolfenite or zircon. I'm not going to show you any of those in the lab. Orthorhombic. Kind of looks like a rectangle, like topaz or sulfur. You'll see sulfur in the lab. Monoclinic, mono meaning 1, so it's got 1 plane that it's equal with, like gypsum and mica. You'll see mica. And triclinic, like kyanite or turquoise. Kyanite, if you think about the name cyan, like the color blue, that's where that name comes from. Elements in the Earth's crust. On your notes, it says, using the slide, label the top 4 elements found in Earth's crust on the pie chart. Then copy down the percentages that appear on the next slide. So in your picture, this section is oxygen. So you need to label that on your pie chart. Here's oxygen. This section's silicon. So the 2 largest sections are of silicon. Aluminum is going to be the 3rd largest. Iron is the 4th largest. Calcium is the 5th largest. Sodium is the 6th largest. Potassium is the 7th largest. Magnesium is the 8th largest. And then you've got this little red section for the other. So everything else that the Earth's crust is composed of is part of that other section. So the big thing to take away from that, oxygen and silicon are the 2 largest. And then on the side of your paper, on the right side of your paper, you already have the key from the slide before with oxygen. You don't necessarily need the symbol. If you're not familiar with the periodic table symbols for the different elements, you might want to copy them down, just so you know, because I will refer to things as oxygen, silicon, aluminum, iron, calcium, sodium, so on and so forth. And then these are the actual percentages. So of the Earth's crust, oxygen composes 46.6% of the Earth's crust. Silicon composes 27.7% of the Earth's crust. Aluminum composes 8.1%. So there's a really big drop from oxygen and silicon. So the majority of the Earth's crust is made of oxygen and silicon, and everything else is just a very little bit. Iron is 5%, calcium is 3.6%, sodium is 2.8%, potassium is 2.6%, magnesium is 2.1%, and then the other category is 1.5%. The mineral composition, there are two major groups. Remember from the pie chart that we just did, the two largest amounts of elements that make up the Earth's crust are silicon and oxygen. So the largest mineral class is going to be the silicates, because that's the most. You put silicon, you put oxygen together, and you make silica, which will make silicate minerals. And then you'll have carbonates made of carbon and oxygen. The silica tetrahedron, remember tetra means 4, consists of 4 oxygen atoms. So you've got 4, 2, 3, 4, packed closely around a single silicon atom, named for its shape like a 3D pyramid. How do minerals form? 3 ways that minerals form. A cooling of molten rock, which would be lava or magma. Lava means it's outside of the earth, magma means it's inside of the earth. Evaporation of a liquid, just like if you were to put a glass of water out for days on end, it's going to evaporate. You get rid of the liquid and the solid's going to get left behind, and that solid can turn into a mineral. And then saturated solutions. That's when you have a whole bunch of a certain amount of something in a liquid. So a saturated solution means you've got almost too much of some sort of additive into a solution. Mineral crystal size. Small crystals indicate Let's try that one more time. I had to correct the problem in the PowerPoint. The crystal size. Small crystals indicate fast cooling of molten rock. Because if you have something really hot that cools really fast, it's not going to be able to make these huge crystals that build on themselves as they cool. So if you see large crystals, it indicates slow cooling. Because the higher the temperature, the longer it's going to take for something to cool. So the more time the crystals have to form. Now for mineral identification. There are a bunch of different ways you can identify a mineral. The very first thing you're going to notice when you look at a mineral is its color. This is the first thing you notice, but unfortunately it's actually the least useful. Just like here on this slide, quartz and fluorite, you've got quartz on the left side and fluorite pictures on the right side. They come in many different colors, so you can't just say that, oh, I see this white thing right here, it must be a piece of quartz. You can't necessarily say that because it could be a piece of fluorite. Fluorite also comes in white. You just don't know. You got to investigate a little bit more past just the color. Hardness is a mineral's resistance to being scratched. There's the Mohs scale of hardness. The scale ranges from 1 to 10, 1 being the softest and 10 being the hardest. And a little factoid, what is the hardest substance on the Earth? Just take a guess. What do you think the hardest substance on the Earth is? It is a diamond. That's why all these engagement rings have diamonds in them. Because a diamond is forever, right, ladies? So if you have a diamond, it's the hardest substance. You actually have to take another diamond to cut a diamond. So a diamond is the hardest thing on Mohs scale. It's a 10 on Mohs scale of hardness. Nothing else but a diamond can be a 10, and a 10 is the hardest for a diamond. And here's Mohs hardness scale. There's 10 for the diamond at the top. This right here is a picture of a diamond. Number 9, so we're starting to get softer as we go down. Number 9, here's corundum, that pink. Number 8 is topaz, that's a birthstone. I think it's for October, maybe. Quartz is this clear white one. That's a 7. It's actually found in glass and windows. That's what makes windows hard, but able to be seen through, because they've got quartz. Feldspar is a number 6. Apatite, just like when you're hungry, apatite's kind of green, it's a 5. Fluorite, just like fluoride that you get your teeth that get put on your teeth when you're younger. That's fluorite. Calcite. This one looks kind of green to me, but typically it's going to be kind of white. This one right here is gypsum. And then this right here is talc. Streak. The color of the powder left when a mineral is rubbed against a hard, rough surface, usually unglazed porcelain. So if you take a piece of mineral on a piece of porcelain and you see what color gets left behind, that's the streak. So right here in these pictures, you're testing a mineral's streak. You've got a red-brown streak of the mineral hematite. This person has the hematite in their hand. They're going across this white piece of porcelain tile, and they're seeing what color it leaves behind. Some of the time, the color that it leaves behind is not the same as the color of the mineral that you see. Like pyrite right here, it looks kind of gold, but it actually will leave a black streak. Luster, the way light reflects from a mineral's surface. So whether it looks shiny, whether it looks dull, you can have a metallic luster where it looks like metal, or a non-metallic luster. And if it's a non-metallic luster, you get all these other fancy words you can use to describe it. It could look glassy, brilliant, greasy, oily, waxy, silky, or pearly. And then here's a picture for metallic luster. It looks like a metal. Pearly luster kind of looks like a pearl. Vitreous would be glassy. Looks like glass. Mineral identification still. Cleavage is the way a mineral breaks along a smooth surface. Whereas if it breaks like a fracture, just like if you were to fracture your arm, that's a jaggedly broken bone. Fracture is going to look jagged when it breaks. Cleavage looks like a smooth surface, like an even plane. Specific gravity, comparing the density of a mineral to the density of water. And we'll actually do this, remember, with the concept for density. We can compare something's density to water, and then we figure out whether it's going to float or whether it's going to sink. And then the acid test. Some minerals give off carbon dioxide when acid is added. When we get into class, I'll actually show this to you. If it's a carbonate and it's got this calcite in it, I'm going to drop oxygen on there, and you can see it get all fizzy. Minerals usage. A mineral ore is a resource mined for profit. If you go to a mine, and at that specific mine they get a lot of a certain type of mineral, that would be a mineral ore, because they're making a profit off of it. They can go sell it. Maybe someone's using that mineral to make something. A gem, a mineral that is beautiful, rare, and valuable. These kind of gems, you're going to find them in jewelry, rings, all that kind of stuff. You're going to want something that's harder if it's going to be in jewelry, so it doesn't fall out, doesn't break, doesn't get lost. Metals are elements that have metallic luster. They're malleable, they're ductile, and they could be conductive. Malleability is the ability of a mineral to be hammered without breaking. Ductility, the ability to be pulled and stretched without breaking. I would kind of think of like a rubber band. You can pull a rubber band and stretch it, obviously to a certain point before it breaks though. And then conductivity, the ability to conduct heat or electricity. If you think about copper, you've got copper wiring, copper pipes, because it insulates things and keeps the heat in. So again, make sure, go back, write down a question so that you can bring it into class.